Hello, I'm Doug Montgomery, and I would like to welcome you back to our Fireside chat for this month. Um, I'm the instructor in your experimental design MOOC, and I've created these Fireside chats because I wanted to have a sort of a live component for our course. Sometimes just watching videos is not exciting. So I thought something like this fireside chat would be something that would be useful and entertaining and informative for a lot of our course participants. Uh, every month I host a session with a guest speaker, and our guest speaker gives a presentation that talks about important topics and real-world applications of experimental design. We always have some time for Q&A when our guest is finished with their presentation. Uh, so whether you're taking the Coursera courses or whether you're somebody that's applying experimental design work in your job, or you simply want to learn more, this is a great opportunity for you to ask questions and engage in some discussion with us. We'd love to have you do that. For those of you that can't join us live, we post the Fireside Chat recordings on our LinkedIn page, which is linked to our YouTube channel. And Nikki Lee, who is the producer of the program, will share that link in the meeting chat. Um, if you're a Coursera course participant, these recordings will also be available in your course under the Resources tab. So that's another way that you can get to them. Quick reminder, uh, please keep your mics muted and your cameras off during the session to avoid any sort of extraneous noise or disturbance that might interrupt the presentation. If you have a question for either me or our guest, please enter that question using the chat function on the Zoom menu bar. And you don't need to wait until the Q&A session begins to submit that. You can start typing that in at any point during our session. And if your question doesn't get answered during this time, we'll get to that later and we'll respond to it in Coursera for those of you that are enrolled in the course. Our guest today is Dr. John Borkowski, and I'm so pleased that we are able to get him here. I've known John for a long time and followed his work with great interest. He was a statistics faculty member in the Department of Mathematical Sciences at Montana State University from 1991 to 2004. He just retired, I discovered, and he's now an Emeritus Professor of Statistics. Which means he's able to do all kinds of stuff like refereeing papers for the journal I edit. So I'll try not to annoy him too much with that. His primary research interest is in the aspect of experimental design that we call response surface methodology. And specifically, his research has included the following topics. One is the use of genetic algorithms and particle swarm optimization for constructing optimal response surface designs. And he's done some really great work in that area. I've dabbled in that area a bit myself. And he's really done some great work. And then applications of number theoretic methods for generation of space filling experimental designs in hypercubes, hyperspheres, as well as simplexes and subspaces for simplexes for mixture experiments, graphical methods for assessing prediction variance properties of response surface designs, and a lot of these designs are very useful for computer experiments. And then finally, applications of classical experimental design, Latin squares, balanced incomplete block designs to generate spatial sampling plans. And John has a really fascinating presentation for us this morning, which I can hardly wait to hear. I'm really interested in this. And John, I'm going to turn it over to you and let you have the floor.
Well, thank you, Doug. And thank you to the support staff for making this happen.
We have a great.
So let me bring up my slides. Okay. It should be visible now.
Yep.
So here, oh, I'm on the wrong slide. Let's start with the title slide. Just a quick outline. I'd like to start with a motivating example for where this actually got applied, these idea of space filling designs. It was a complicated problem. Then we'll look at a a little simpler problem also as a motivating example. Um, Describing the type of problems, applications, and then get into the actual numerical measures for how you assess space filling properties. And I'm going to focus on one particular one just for this talk, but there are multiple other ones. Actual methods. How do you generate the points that are space filling? There are different methods for that also. I'll cover 3 of those. And then generalizing those or extending them to other regions, because the ones I'll be showing you initially are really in rectangular, hyperrectangular regions. But what if you want a space filling design in a spherical region? Or maybe in a simplex or subspace of a simplex and used in the mixture experiments. And then finally, a short summary. So this was the example that motivated my initial work in this, and it was about 15 years ago. Suppose you have enough resources to collect 50 experimental mixtures, and they want to have a good space filling properties. Right now, I'm using this term very generically, space filling. I think each of you out there might have a different idea what that means. We're going to quantify that in a little bit. But the problem is very complex in the sense that the mixture had 16 different components in it. The idea was to make this waste glass. It's called a vitrification process. Each of these 16 components has upper and lower bounds on them, constraints. Because it's a mixture component, these are proportions. They will sum to 1. And we have these lower and upper bounds. We'll denote them Li and Ui for each of the ith component. And here are the actual bounds, the in particular mixture components. There's, you can see the 16 of them in the table. And the bounds for each. And you can see this is in 16. This is in a high dimensional space, and you're slicing and dicing this simplex. And to make it even more complex, I'm not going to get that part today, but there were also 8 multiple component constraints, linear combinations of these components. And the idea was to collect data. We only had resources for 50 experimental, again, mixtures, and these were quite expensive. And so this is work I had done with Greg People at the Pacific Northwest National Laboratories when I was a part of one of my sabbaticals. Let's take a simpler case, one that you might see more in a textbook. You want to model a relationship between 2 quantitative variables, temperature in degrees centigrade and time in minutes. And your response is the hardness of a certain plastic in some manufacturing process. There are upper and lower bounds set for the temperature, say between 100 and 200 degrees centigrade, and time between 30 and 60 minutes. So you really have a rectangular region here. You just think about putting the separate bounds on each of those. So you have a ranges of 100 degrees for temperature, 30 minutes for the time in minutes. What I'm going to do is code these between 0 and 1. In a lot of response surface books, and you might see them coded between -1 and +1. But because we'll be working with these certain types of numerical number theoretic methods, that we'll code them between 0 and 1, and then we'll back transform them to the original scale so the experiment can be run in terms of temperature and time. Maybe a couple things could happen here. Maybe the researcher wants to consider different models, classic polynomial, like second order response surface models, or maybe nonlinear models found in engineering literature. Things like this Michaelis-Menten models and these other models that appear in engineering literature, as well as maybe pharmacokinetics. You'll see lots of nonlinear models. Or you might use these also, as Doug alluded to, for possible computer experiments. And so what we're going to look at is an example here. Suppose this researcher can collect 23 experimental runs in terms of the temperature and time. And in the same region I referred to for temperature and time. And here are 23 pairs. And they say they're coded between the 0 and 1. It looks pretty good in terms of maybe what you consider as space filling. Well, it looks pretty good. The points are scattered throughout the region. But we still haven't introduced any criterion for assessing space fillingness. But in general, you can think of it, you don't want points to be close to each other. You don't want them all clustered together. You don't want to see big empty spaces in your region with no points in them. So a good space filling design for this problem, they're going to collect data in that region, the 0, 1, 0, 1, and then we'll go back to the original scale. So this is an example. If you took those 23 points I just showed you in the previous slide, the coordinates, the x1, x2 coordinates, you can see in the first 3 columns there, they're the 23 points and the coordinates. You can see they're all between 0 and 1 for both of the coordinates. We back transform the temperature and time. Those would be the experimental levels in which you would collect the data. Typically, I mean, you would randomize the order of these, and you'd collect your measurements. And you have, in this case, the response was the hardness of that plastic. And at that point, I'm not going to be focusing on the data analysis part, but I'm focusing on the actual experimental design part. But once you have the data, you can think about fitting different types of models. These are things that the research should have thought about ahead of time, the type of models, or you can use this data just to explore the region. Where is like a sub-region where I might be getting a good response? I mean, if hardness was a good, if you want a very hard plastic, you're trying to find maybe a sub-region within there that would give you a good hardness response. So simple description. Everything I'm going to use examples just in 2 dimension because they're nice to visually. But everything I'm doing, and I'll comment on this, can be extended to any dimension. 3, 4, 5. You have more than 2 factors in your experiment. But just visually, I'm just going to stick to 2 for this experiment, but I'll show you how to generalize it to higher levels in terms of dimensions. So if we have 2 factors, once they're scaled, they'll be between 0 and 1. So we have a square, a unit square. And we want to put endpoints into that square that are space filling. So the endpoints should not appear together. They should be spread throughout the region. I'm going to show you 3 methods of doing that. 2 of them are based on what's called uniform sequences, and one is called the Good Lattice Point method. But there are others out there. So pretty obvious. If you look, I have 4 cases here of 14 points in the unit square. It's obvious in the upper left, this is not good space filling. You have a large empty space. The second one, you tend to have clusters. So clusters may be spread throughout the region, but the clusters, you don't want them. You want those spread out more. And then you have the 2 on the bottom. You have, I call them better space filling. You can see that they are more spread out throughout the region. But when it comes to picking one, you need a criterion. Which is better, C or D? Or they may be equally as good. So we take those 2 designs, and we're going to need, you'll need a numerical measure, well, several measures if you want to look at more than one, to assess the goodness of the spread in the space filling properties. So we're going to introduce the concept of a distance between a point and a set here. So I said here, let U1, U2 be any point in that unit square. And the script X there is the set of the points that are in the design. So, and we talk about the distance between a point and a set. Then when you use that notation, I have D, U, and X is the difference between U and the nearest point in the design. So this was that bad design I showed you earlier with the 14 points. If this was my point U, if like you could look at the points here, the 3 different points U1, U2 identified, and then you see the line segments going to the nearest point in the design. So you see 3 different distances. Every point, there'll be a distance associated. And what do you want? You want to have that distance small. One criterion is just, let's make the worst case as good as possible. So there's an assortment of measures for assessing space filling properties. two of the most common one, the one that occurred, uh, what I first saw was called discrepancy. Um, I'm going to focus on the distance based, but I'll give a couple of references below if you want to look at discrepancy. I prefer distance-based methods because discrepancy, um, there are some issues with it. And I can always talk a little bit about that later. But I prefer the distance-based measures. And I'm going to consider just one, the maximum distance criterion. But there's also the average distance, the square root, the mean square distance. So there are other criteria out there. They tend to be they're very highly correlated. What's good by one often is very, very good by the other. So I'm just going to focus on one, but there are other measures out there. Fong and Wang, I want to make a quick comment about that. That is the first source I read that really got me interested in this. And I don't know if I can hold it. It's probably going to block. It's probably the screen is. Oh, it's not going to work with the because of the background. Okay, but oh, there I can do it that way. Um, this is the book that I really got interested in. It's the Number Theoretic Methods in Statistics. And that's where I was introduced to a lot of these different methods. And then Greg People and I worked on the paper together in 2009 for that mixture experiment. And then I had a PhD student, Ishmael Taki. We had published a couple of papers plus his dissertation. And they provide good overviews on the different measures that are out there. So for a distance-based measure, what we're going to do is we're going to look at the criterion. We're going to define, again, we have a set of points that if they have good space filling properties, then the distance between any point in the unit square to that set of that design point should be as small as possible. Well, one way we can think about that is, again, the maximum distance is one criterion. So you want to minimize the maximum distance, so minimax criterion, minimize the maximum distance m, where m is the maximum distance between over the set of all points in your space, design space, and the design. And I mentioned a couple other ones. You could use average distance or root mean square distance as a criterion. So here's an example, that bad kind of design I showed you before. We have this large area without points. The point on the left axis, the x2 axis, is the point which is furthest away from the nearest design point. All other points in the space are closer to one of the design points. So that would be your criterion. It doesn't have to be unique either. In this case, that point is equidistant from 2 points in the design. But that m is the criterion. And you want to keep that as small as possible. That would be, again, one criterion that I'll be focusing on just for this talk. As you can see here, here's 23 points. These are certainly clearly better space filling. You don't see big open areas where there's no data points going to be collected. It has good space filling properties. I also indicate that red diamond is the point which is furthest away from the nearest design point in the square. And that would be the criterion. And again, that's what you want to try to minimize. Now, that's a criterion. Now, how do you generate these points? I showed you sets of points. How are they generated? First, we're going to fix the design size. Suppose we want to collect n experimental design points. So we're going to code them and put them in the unit square and then back transform them. So we want to find a set of points, that script x, that minimize the maximum distance. I'm going to show you 3 methods: powers of a prime, square root sequence. So those first 2 are based on what are called uniform sequences. And the third one is called the Good Lattice Point, which is a much more discrete, it's not based on a sequence method. There are other methods called the Halton method, Hammersley method, based on these p-adic representations of numbers, cyclotomic fields. I had to read I have no idea what these originally meant. I didn't know idea what a cyclotomic field was until I started reading about these. And that one involves decimal expansions involving cosines. You see these references are quite old. I mean, these are over 60 to 65 years old. The thing is, these were not used by statisticians. These were developed by mathematicians. And they were used to generate sets that can be used for numerical integration. Uh, if you want to find the average value of a function, you can generate these sets of points, and you can take averages over them to get a good approximation to an average value of a function. But they were developed by mathematicians, and it wasn't until I saw the Fang and Wang book that I started seeing those applications to statistics. So this powers over prime method, I want to preface this by saying these are almost embarrassingly simple methods. They involve, if you can work with prime numbers or cosines or anything, you can do these methods very simply. So we're going to start with the first one. So powers over prime method, PMP. Take a prime number, any prime number. So what we do is to generate a set of n numbers in the unit square using this method. What we do is, for the two-dimensional case, take that prime number to the third power, that prime number to the two-thirds power, form a pair, and then multiplies by those by 1, 2, 3, 4, up to n. So we'll have n pairs of points. And then just keep the decimal part. Throw away the integer part and just keep the decimal part, and you will be between 0 and 1. So if you want to work with higher dimensions, maybe you have 3 factors or 4 factors in your experiment, you just take the prime and you raise it to the s plus first power, then you square it, you cube it all the way up to the s. So you would have, instead of 2 generated, instead of a pair, you'd have an s tuplet, and you'll generate an s tuplet between 0 and 1, a set. So simple example here, 14 points. Suppose we took 2 as our prime number. So we would look at 2 to the third, 2 to the 2/3, multiply each of those by the 1 through 14. So that's the step 1 here. If you look, the first column is the 1 through 14. Multiply the 2 to the third, 2 to the 2/3 by k. You get these numbers like in the column there, 1.2599 down to 17.6389, and similarly for the third column. And to finish it, we just throw away the decimal part. So just keep the fractional part between the 0 and 1. And that's where you see the last 2 columns, step 2 and 3. And you get pairs of values that are between 0 and 1. And if this was a good design, you could then convert these back to original time and temperature to run an experiment, a space filling experiment. The problem is some primes work better than others. And so it's kind of a trial and error. And I'll talk a little bit about why about this. That you don't know, you can't figure out ahead of time which is going to be the best. And I'll explain why in a little bit. But here are and you tend to work with the primes that are less than the experimental design size. You can work with them larger, but the research, we never found any that work. The smaller ones always work the best. So here I just show you, if you started with p equals 2, which is the one I just showed you the table for, the upper left is the 14 points, generally using the square root of 2. Sorry, 2 to the third and 2 to the 2/3. And then the second one in the middle up on the top, that's where I use 3 to the third and 3 to the 2/3, 5 to the third and 5 to the 2/3, and so on, up through the 6 different primes. And again, you can see they're kind of spread out. Some are going to be better than others. It looks like 11 might be bad because you got quite an open area down below, but we'll apply the criterion. Which one of these is best by that maximum distance criterion? Now, here's one of the issues involved here is to find, there's the way that I initially did this with Greg People and with my students. You're trying to find a point in a continuum that gives you the maximum. One way you can get a very good approximation to that value m, that maximum distance, is just take a very large random sample in the square, say 10,000. calculate them, find the maximum distance for those 10,000, and then use that as your estimate for M. Later on, I'll talk about some research I'm thinking about for making this a little bit better, but this works really well. And in this case, 5, prime 5, generated the best one. These were you can see the 6 different primes, the P column, and then I sorted them from best to worst. And the best one was 5. And you can see the points are quite well spread out throughout that region. And they said the worst one was 11. And we saw that before on the previous slide. 11 was the worst one. You can see that open area there at the bottom, whereas P is 11. You might get a little better approximation by using more points. I mean, shooting wise, takes minimal, very small amount of time to do 10,000 points and find the maximum distance. Let's go to the second method, the square root sequence method. Here we're just working with square roots of prime numbers. Again, very simple to do. However, whatever your dimension is, take that many different prime numbers. So if I'm working in a square, I take 2 prime numbers. I'm in a cube, take 3. Higher dimensions, whatever the dimension is, take that many different prime numbers. Take the square roots of each of those prime numbers. Square root of P1, P2, for the 2-dimensional case. Just like we did before, multiply each of those by the numbers 1 through n. We'll get n pairs of points, and like before, throw away the decimal part. Just keep the fractional part. And so for in s-dimensional case, you work with s different primes. So the 2-dimensional case, suppose I just use square root of 2, square root of 3, the first 2 primes. So we have the k column, multiply square root of 2 by k. You got then square root of 3 by k. So like the square root of 3 by k, and you have the numbers going 1.7321, rounded to 4 decimal places, up to 24.2487 in the third column. And we just throw away the decimal part. Sorry, the integer part, and save the decimal part. And we get numbers between 0 and 1. The reason partly why these are working, but these are irrational numbers. These will never repeat. You'll never get the same 2 points again. It's impossible. If you took the full decimal expansion, I mean, you just keep going with the decimal places, you will never get anything repeating. By working with square roots and powers of primes, you will get unique sets of points. So in this problem, I took the first 5 prime numbers, and there are 10 pairs, 2, 3, up to 7, 11, and then I put them in, and I sorted them, found the M criterion for each of those 11 pairs of primes. The best one was 2 and 11 and 5 and 11. I have them both highlighted because if I took another set of 10,000 points, it is certainly possible that they could switch. They're same to the third decimal place, but they are so very, very similar. But you can always increase the number of points if you want a little bit better approximation to that M. But certainly there's separation between those two and then the next couple and all the way up to the 7-11 case, which is very poor. So these generate quite good. And now you can actually look, when you start thinking about this, I can generate a design using the Powers modular prime method. I can generate a square root sequence, and I can compare those M values directly. I can compare within a method and across methods. The distances represent the same thing. So you can, and what I find interesting about this research too, and these methods, is one method is not always the best. Square root sequence may be best one time. The Powers modular prime might be another time. We'll see the third one might be the best. And other times, this Good Lattice Point method. So that's why we look at multiple methods. And that's why at least my PhD student, they were all tabulated. So what the best designs are for these different methods for designs up to 50 points. So you can always find those in the publications. You don't have to reinvent the wheel here. So a little bit in terms of the third method, the Good Lattice Point method, the GLP, has direct relationships between Latin hypercube sampling. You'll see that, and if you're familiar with that, you'll see that shortly. But before we get to the method, just one definition. Two numbers, integers, are relatively prime if their greatest common divisor is 1. So if you take their prime number expansions, they have no primes in common other than 1. I mean, other than 1 is a factor. And so what we do with this method is different than the other ones. We just don't keep multiple. We have to work with what's going to be permutations. So to generate a set of n numbers in that unit square using this method, just for two factors, you just need one number that's relatively prime with the sample, with the design size. Find some positive integer h, which is small, which is less than the design size, which is also relatively prime with it. And we'll look at an example in a minute. And then we take that and we multiply that number, which is relatively prime, by k again, 1 through n, just like we did in the others. And we don't throw away the decimal point. What we have is a ratio. We set up a number here. What we do is use modular arithmetic. Take the products and divide by n and keep the remainder. So those remainders will be between 0 and n minus 1. And then what we do is step 3, we create these rational values, 2k minus 1 over 2n and 2r minus 1 over n. It's easy to see with an example what's going on here in terms of that modular arithmetic. So for example, suppose there's a typo here. That should be h equals 5. So I have 1 through n, 1 through 14, hk. So it's 5 times 1 through 14. So you get the values here. Divide each of these by 14. What's your remainder? Well, the first column, remainders are just the values themselves. And what'll happen is if you get a 0, when the remainder is 0, you set it back to n. That's the way this method works. Any 0 is set back to n. And then you can see the column with 5k mod 14, like 15 is 1 mod 14. You divide 15 by 14, you get 1 times 14 plus 1. These are all the remainders. And that is what's important is that it be relatively prime. By being relatively prime, we are forced to get a permutation of the first column. You can never see the same two numbers. If it was not relatively prime, you will see the numbers appearing multiple. You'll see the same value appearing multiple times in that column. The relatively prime is important to make those unique. So that column is just a permutation of the numbers 1 through 14. And then we scale them, so they're between 0 and 1. We take the 2k minus 1 column, divide it by the 2 times the design size, 2 times 14, 2 times the r column, minus 1 divided by 28, and we get values between 0 and 1. And so every number you see in the first column here, in the x1 column, is also going to appear in the x2, but it's just a permutation of it. So if we had 14 as our design size, there are 5 numbers which are relatively prime to it. 3, 5, 9, 11, and 13. Can't have any even numbers because they'll have 2 in common. So we have 5 possible good lattice point designs using for 14 points. And again, I would generate 10,000 points, find the maximum distance. So here's a picture of the 5 different designs. And I put them again in order of the best to worst for that maximum M criterion. As you can see, the 9 and 11 are very, very similar, the 0.26. And what we've actually shown mathematically in the research is some can be equivalent to each other. They can just be rotations of the other or reflections of the other. So they will give you the same M value. You might get the same criterion. So you can pick either one in terms of its space filling property. But then other ones get worse. And then finally, You can see the one on the bottom right is just a horrible design. But that's what it would generate if you use 13 as the relatively prime number. And I can tell you right now, never use the design size -1 as the relative prime number. You'll always get this type of pattern, just a bad design. So now, the general question I was asking myself, okay, why are some better than others? And why do these methods only sometimes yield good space filling points? Maybe sometimes they have some bad designs. The first two methods, and this is going to be focused on those first two methods that are based on these called uniform sequences, and they're related to limits. And so let's look at a case where, because with those first methods, we can make n any size. We're just multiplying 1 times like this a cube root of 2, 2 times a cube root of 2, 3 times a cube root of 2. We can do that forever, but we truncate at n, the design size. So let's look at the modulo prime method, powers over prime method with prime of 2, square root sequence with P1 and P2 being these two primes, and we're going to generate a couple of points. So I just have to change the sharing. I want to show you a short video here. An invalid screen. Let me go back to the presentations. What I'll do is if I have a little bit of time later, I'll come back to this. Sorry about that. The main thing is, what'll happen is when you generate points by this method, if you wait long enough, they will fill in the entire region. There will be the points, the criterion, the maximum distance criterion goes to 0, the larger n gets. The problem is you don't know how long it's going to take to really observe that kind of convergence. We are stopping at a fixed point in time, so we don't know which method is going to be best for smaller design sizes. But if you wait long enough, they're all equally good in terms of their space filling properties. The good lattice point is it's not based on a sequence. You have to find a different permutation for every n. So am I, okay, I'm sharing. So the main thing is that criterion goes to 0 as n goes to infinity. And so we're confident to have a good space filling set of points if we wait long enough. But in practice, we can't do that. We have a fixed budget. We can only generate endpoints. And we compare methods, and we take the one which has the best criterion. Now, the one thing that I found interesting about these methods, too, is the fact that you can generalize these to other regions. Suppose you have a spherical design region, which is maybe the case when people work with central composite designs. You might work with rotatable designs or points where the axial distance are out to a certain distance, like the square root of the number of factors. You're working in a spherical region. Well, I just have not seen very much work done in terms of space filling designs in spherical regions. But what we can do here is we just need to map from the cube or the square into a spherical region, recalculate our criterion, but in the spherical region space. And the thing is, these are nonlinear transformations. So what's best in the cube is not necessarily what's going to be best in the sphere after you transform it. So you have to, and that was the one thing that I kind of disagreed with the book with Fang and Wang is they just say, oh, transform them and use that design. Find the best one in the cube, transform it and use it. I said, no, my approach was transform, then you got to recalculate that distance criterion because of the nonlinear transformation. And for 2 dimensions, if you take x1 and x2 between 0 and 1, and you define your theta, your angle, to between 0 and 2 pi by doing 2 pi x1, and the radius, we take the square root of x2, which is, we use the square root instead of just x2 because how the area is increasing with the square of the radius. So this keeps them spaced out properly by using the square root. In higher dimensions, you can use hyperspherical coordinates to map from from a hypercube to a hypersphere. And here's an example. Suppose I use this powers of a prime method. And I used three different primes, like 13, 5, and 7. The three upper designs, you can see the designs in the square. We use that polar coordinates transformation. It maps them into the circle. Then once they're mapped into the circle, calculate the distance criterion inside the circle, the M. And the best one is going to be the 13 of these three different ones. You kind of start seeing that spiraling shape, which corresponds to those sort of diagonal lines diagonal sets of points that you see in the square. Very simple idea. Again, you find the designs in the square, map them to the circle, calculate the criterion, take the best one. And you can do this using good lattice points. You can use it doing square root sequence and to find a good space filling design. And the final topic is, and this goes back to the original problem that I mentioned, a high dimensional problem with the mixtures. So in your mixture experiment, we're just assuming the simplest case where the response depends upon the proportion of the components and not the amounts. There are mixture amount problems, but we're not focusing on those today. Again, a mixture, there are proportions of the components, so they're between 0 and 1, and they have to sum to 1. If it satisfies these constraints, it's going to be in a simplex. Maybe the researcher's goal is to eventually to predict the response for any mixture, find some subspace of that simplex to maybe experiment more to get where you might get a good region where you get a good response, maybe a maximum or minimum response. You might want to fit models. And again, you can fit, with these type of designs, you can fit many different types of models that can be the researcher might want to consider. What's more common in mixture experiments is you're going to have constraints on those upper and lower components. Like, for example, if you want to have a cup of coffee and you can think, okay, I have coffee, I have milk, and I have sugar. I have three components. I have to have a certain proportions of each. Well, I can't have a cup of coffee with 0% coffee. I mean, there's got to be at least a minimum amount of coffee that's reasonable. You can certainly make a black cup of coffee with 100%, but there's often going to be bounds that make sense in a problem between a minimum and a maximum of each of the components. And when you do that, you start getting these irregularly shaped polyhedrons inside the simplex. And for example, the one I have below, the 0.2 to 0.6 for x1, the 0.1 to 0.6 for x2, 0.1 to 0.5 for x3. It's the experimental region would be inside that green irregular hexagon. And you would try to fill in that space. A bit harder than the circle where you just do the polar coordinates. So how do you do this? Very similarly, we are going to generate points like we did before in a square or a cube, whatever your dimension is, and then we have to map them into the simplex. What was interesting about this, it was in the Fang and Wang and their research provided a mapping, a one-to-one mapping between the Q minus one dimensional space and the simplex, the Q component simplex. And you can find that also in the paper with Greg People and myself. So here we have 25 design points in the square. You go below. That transformation presented in that paper showed this would be the 25 points that we mapped into the simplex. You have the 50 points on the right mapped into the simplex. And then once you're in the simplex, you can use a distance measure to find which one is, you might have multiple 50-point designs, which one is best. But again, it's a nonlinear transformation. You start seeing the points get bent or curved. But like the one on the right is still quite like pretty good space filling properties for the 50-point design once you apply the transformation. And to finish with a look at this three-component mixture which has lower and upper bounds, 0.2 to 0.6, 0.1 to 0.6, and 0.1 to 0.5. And you want to generate 17 point, you have enough resources to collect 17 mixtures in that space. And if I use the good lattice point method, there'll be 15 possible generators. If you're looking at 17 points, the numbers 1 through 16 are relatively prime. to 17. So there are 16 different pairs of generators. And again, I have them sorted from the best to the worst here. And I'm going to, the next picture, so 1.5 and 1.12 and the 1.4 are the best. The 1.2 and 1.9, 1.16 generators generate the worst. And these are the three best and the three worst cases. The 1.5, the 1.12, and again, you can see those are generally pretty good space filling properties inside that constrained mixture space. Again, these transformations could be used for any dimension. I'm just showing you for the three component mixture problem. And the ones on the bottom, again, you can get just a bad case for the good lattice point method for several different generators. But again, it's kind of a trial and error. You got to look at each. But again, these have been tabulated. So, that's a good point I want to make. These have not been tabulated because you get different sets of constraints. You'll get different generators. The results have been tabulated for the full simplex, but for the subspaces of the simplex, you do have to kind of work it out yourself and find the best one given those sets of constraints. So to finish, and I'll make one short attempt to try to get the video back. A space filling design, I mean, they can be used by statisticians to design experiments, produce useful information to fit and compare different statistical models. As excuse me, as Doug alluded to earlier, they can be used for computer experiments too, as inputs for computer experiments. I showed you three different methods. There are others out there, but these three seem to work quite well. We can generate these to higher dimensions, like into cubes, spheres, hyperspheres. Some current research that I was involved in is involving these interesting space filling designs for mixture process variable experiments. So maybe and you have the three component mixture, but maybe you want to do at different mixing speeds or different temperatures. You have quantitative variables. And what would distance mean when you have that kind of hybrid type of design? And I had a former PhD student work on those. Also, if you want the idea of maybe look at two criteria simultaneously, maybe have designs where space filling, but have also good efficiencies in terms of fitting specific models, like a second order polynomial. So that's some research to look at too, is to have these hybrid designs, possibly involving Pareto fronts to try to find possible good designs on related to those. And the final comment is, I didn't put it up here, but I'm thinking about also and see if it's even worth the effort. Instead of using like 10,000 points to get it, the value for the the maximum distance, to use something like a particle swarm to find the actual point that gives you the maximum distance. So you get the true value, really the true value as opposed to an approximation. I doubt it's going to change very much, but I just find it interesting to see how close they really are to the theoretically best. But that involves a whole nother layer of computation to do that. And the final point is possibly also use like particle swarm optimization. Take one of those good designs that are out there and perturb the points a little bit. Let them move around a bit and maybe improve the criterion a little bit more. Instead of just sticking with the designs generated by the number theoretic methods, take those and then perturb them to improve the criterion and improve improve that. So I will end there. Thank you for again for this invitation, and just a few references. Not a long reference list for this talk, but you'll see the Fang and Wang and a couple of papers that I worked on and a couple of things on uniform designs. So I will stop here, and I will just make one last attempt.
Yeah, I'd like to see the video.
Yeah, I had it ready. I'll start this from the beginning. Let me go to the beginning for this slide. So I was using two different methods to generate points in the square, the powers modulo prime and then the square root sequence, not powers of a prime. So, and so the two different methods, this is like the first set of points that might be generated. I don't know the exact number here, maybe around 20. And there are different locations, they'll have different M values. But if you just like keep increasing, let the sequence go on and on, you can see they start filling the space in different ways. They have these different patterns. You start seeing these clusterings, different patterns forming, but oh, go back to the one. There we go. If you wait long enough, they're going to fill in the region. These are called that uniform sequences. It's just that some methods fill in a little faster than others. And if you wait long enough, I mean, for large enough design size, that M will go towards zero. And the same thing could be if we worked I like the simplex problem. We stop it. So in the upper left, we have the points in the square. They're getting matched on the right, you see the full simplex. And below that is a subspace of the simplex where you have upper and lower bound constraints. But it's a nonlinear transformation. But again, if you just wait long enough, it's going to fill in the square, but it's also going to fill in the simplex and the subspace of the simplex. In terms of, and here's one for the circle. And the upper left is the points in the circle. You do the polar coordinates transformation to the circle. And you can start seeing how they get mapped and how it starts filling in the space, these uniform sequences. But again, we have a finite n. We are truncating that sequence. We don't know how good it is space filling, but in the long run, it's going to fill in the space. And that's why if you have a lot of points, you can get very good approximations to functions. And I do like that mapping, to show that mapping, how it works. So that gives you some idea what's going on with those sequences. And we're just truncating them after a certain design size. Okay,
Fascinating.
am I back?
Yep.
Yeah, it's these mathematicians back in the early 1960s with all used for numerical integration. And then Fang and Wang, they come out with some papers. They were all in Chinese, the original papers
Okay.
in Chinese journals. And then they got translated, and he pretty much took those papers and put them in form of a book.
So the book
Um,
was kind of just a compilation of the papers.
Mostly, yeah. A
Yeah.
few of them were in English uh, language journals, but the original ones were all in Chinese journals. I had a graduate student from China. She helped translate a couple of the original papers for me.
Wow.
Yeah,
Great.
yeah.
John, we have a question that just popped up on my screen.
Okay.
Um, I don't know that you can see it, but let me read the question. Uh, it says,
Oh, I can see.
was the mapping from hypercube to simplex done on the full domain, and then points that violate constraints are removed? Or were the constraints mapped
Ah,
backwards onto the hypercube and the design points created on the constrained region then mapped to the simplex?
great question. Um,
Yeah.
no, they are not. It's not like an inclusion exclusion type of thing. Um, uh, for the oh, there's two answers to this question. For the one that I showed you, where you just have upper and lower bounds, they are getting mapped directly from the hypercube into the simplex or subspace of the simplex. There's a mapping, and it's based on conditional arguments. Given that you've selected the first component value for it, then it affects what possibilities there are for the second, the third, the fourth. It's a sequence. You're doing it sequentially. You find one, then you find the second component. Now you have the first two components. What possible values are there for the third component, and so on. So it's a direct mapping. When it came to the original problem with Greg People, we had multiple component constraints.
Mm,
And there, what we did, we essentially did the mapping based on the single component constraints, and then threw away the points that violated the multiple component constraint assumptions to get the design size we wanted. I've seen no way to directly to map into a subspace that's formed by multiple components constraints. It's an interesting research question if it can be done, but I've not seen anyone even really publish
I
anything attempting
I
that.
kind of think that would be a very hard thing to do, John.
Yeah, but what we did work quite well. Is we it was kind of you had to try different approaches, but we got the design size we wanted that met all the single and multiple component constraints
Right.
and with space filling and calculate the criterion.
Very nice. Um, One of the questions that sort of occurred to me uh,
Mhm.
as you were starting into this, but which I think you've answered, what about constrained regions? And obviously, your mixture space are constrained regions, but you could also have a constrained region on hypercube too. You
Oh
could,
yeah, oh definitely.
yeah, you could have one corner of the thing knocked off because there's certain levels of time and temperature that you can't run because it blows the place up. So
Blows up, yeah.
yeah,
It
right,
explodes. Yeah, it doesn't even form a
right.
product.
So that's always the classic example I use in class. Is the reason you have these constraints is because if you run these time and temperature combinations, you blow the place up. Career limiting move for most people. The
Right. And yeah, definitely in the or if you had a slice, same thing in a spherical region, you could slice the sphere
Right.
somewhere to be
and
constraints on the spherical region.
and so
And one thing I
you toward the end of the
had,
talk, you sort of mentioned uh, mixture process type experiments. And are you currently got somebody working on that or uh,
I have well, I had the student as part of his dissertation,
okay,
Moses Obiri, who now is working at PNNL, Pacific National Laboratories.
okay,
Um, uh, we need to get a couple of these papers out, but yes, it was a kind of a two-step process. In terms of working with mixture process, you want to have the mixtures. Imagine you have if you had a three-component mixture problem and you had one quantitative variable, your design region almost looks like a prism,
mm-hmm,
a quantitative variable. And you're trying to get kind of space filling in that type of region. So we had to really work with trying to get good space filling in the with the simplex, and then try to extend it to the quantitative variables. And yeah, we got some good results there.
good. Another question
Yeah,
popped up. It
okay.
said, this question says, what would you do if your constraint creates holes in your design space in a high dimensional space? Do you think you could always find a mapping?
No. I don't. Well, it depends on the shape of the region, I would think.
I think so.
But yeah, I would think, of course, if there was some reason like a hole, you had a sphere with a hole in the center. Um, I can't think of doing like a direct. Well, that could actually probably be done, where your radius goes from some positive value to an extreme. Um, but in general, in those type of problems where I believe there's a hole, you almost have to, like we did in the original paper with the mixtures, is do kind of an inclusion exclusion, generate a set that meets all the one set of constraints, or it fills in the entire region, and then remove the points that don't satisfy or that are inside that hole.
Right.
And it should be space filling in the remaining portion of the design space, like a donut.
Yeah.
Um,
Yeah.
and again, you would not take the design that's best in the circle. You would take those points that are in the donut and calculate the distance between all points that are in the donut to the nearest design point,
Right.
and work that way. That's a good question.
Yeah, that is a good question. So I have one last question for you. And it's a
Okay,
question that John, I get asked this all the time. Okay. Uh, and with these,
where's Montana?
no, it's usually in the context of these space filling type designs for computer experiments. And that is, how many runs do I really need to make in order to get good results, good space
Oh,
filling properties? And I have a rule of thumb that I use. And rules of thumb often lead to your thumb getting cut off. So it may not be a good rule of thumb. But I tell people that the minimum is about 10 per variable. So if you have a two variable problem, I'd like to see 20 runs. And if you have a three variable problem, I'd like to see 30 runs. And the only
yeah, the
problem
curse of dimensionality.
the only problem with that is I get pushback sometimes. They say, well, each one of our runs on our computer model takes 3 hours. And so anyway, what sort of answer do you have for that question? That always bugs me.
What I've thought about that, yeah, that's just a tough question to answer. But what
It
I've
really
thought
is.
about is the idea of multi stages, multiple.
Yeah.
You could start with a smaller design, and
See what happens.
then you can see results, and then you can augment it.
Yeah.
If your goal is depending on what your goal is. If your goal is a maximization, and you could try to search in a region, you might reduce the region you search in, or yeah, you can start filling in a smaller space. You can do a second set of points, which better fill in maybe some uh,
Yeah. Some
optimistic region
some area you're interested in. Sure.
you're interested in. Start with something, and so you kind of get a big global, and hopefully, like one of the initial design points is in the region where you can then hone in on a true optimum.
Yeah.
There are maybe regions that are just, oh, there's no reason to collect any more data over there. There's just and not waste your time on the computer for these 3 hours. Start focusing on subregions for the if you had 20 points, maybe start with 10 and then maybe go 10 to a smaller region. I've thought about that. I've never had to apply that, but that's the logic I had in my mind when I thought is thinking about some of these problems, which you have really worry about your budget and time. I
John,
don't know if that makes sense to you.
appreciate all of your contributions here today. Sadly, time is up, and we're going to have to abandon ship here. But I really appreciate this fascinating talk. I really enjoyed every minute of this, and I hope you enjoy your retirement and don't stay away. Okay.
Oh yeah, I won't.
Okay.
I'm busy.
Take care. Thank you.
Thank you. Thank you very much.